Good morning. We're going to begin our unit on equilibrium. We're going to start by looking at the general equilibrium, how to set up equilibrium expressions and make calculations to determine the equilibrium position. We'll then focus on the factors that affect equilibrium, and we'll finish with solubility equilibrium, where we'll look at insoluble salts and see the extent to which they will dissolve in water. A chemical equilibrium is defined as a dynamic change that occurs when the forward and the reverse reactions are occurring at the same rate. So therefore, your concentration of reactants and products are no longer changing overall. You just have them occurring at the same rate, so you see no net change being observed. We first discussed the idea or the concept of a reversible or equilibrium reaction back when we were talking about equilibrium vapor pressures, when we were talking about boiling points in our solids and liquids unit. When we look at a reversible reaction, it is signified in a chemical reaction by using a double-sided arrow instead of a single-sided arrow. We had always assumed when we first started our talk on chemical reactions and stoichiometry that we would always have 100% reaction that would occur between two or more substances until our limiting reactant ran out. But we came to realize when we were talking about our percent yields that sometimes those reactions stop short of completion and will actually be an equilibrium system. Now, again, from a chemical reaction standpoint, remember this is that collision theory concept that we had talked about. You have initially a large amount of reactants, you don't have any products, and so typically with those types of systems, you have a very high reaction rate in the forward direction to begin with, but as that concentration drops, the rate of the forward reaction begins to decrease. But at the same time, we now have products being produced, so you start to have collisions occurring between the product molecules, and they can go back and reform the reactants. And so eventually, when those rates are equal to each other, that's when you have the equilibrium take place. Just understand, equilibrium has nothing to do with kinetics. How quickly that reaction occurs is irrelevant to the equilibrium system. Whether it takes 3 seconds or whether it takes 30 years, it only matters when that forward and reverse rates are equal to each other. You can see here with these two graphs the illustration of the equilibrium concept. The graph on the left, again, we talk about the kinetics happening on the left side of the graph. You'll notice that the concentration of the N2O4 begins to decrease and the concentration of the NO2 begins to increase until we hit that dotted line where the concentrations now have leveled out and we have no change in concentrations. Therefore, the equilibrium has been established. When we look at this chemical reaction, we have N2O4 forming 2NO2. You'll notice that the change in the concentration for the N2O4 is about half of the concentration change for the NO2. And that bears out playing with our coefficients. So again, you have your concentration changing until at some point there's a constant concentration within the system that allows you to know that the equilibrium has been established. When we look at the rate versus the time, now you can see here these two graphs will always converge because the rates have to be equal to each other. And so you have the reverse rate starting to pick up and increase. You have the forward rate beginning to decrease until that point in time when the rates are equal to each other. And so at that point in time, we now have equilibrium being established. So here's a picture of that reaction that we were just discussing on the previous slide. You'll notice in this first picture on the left that there is just a very faint brown color within the bottle, meaning that there is just a tiny little bit of the NO2 that has formed. The N2O4 is a colorless gas. The NO2 is a brown gas. So as the reaction proceeds, you can see that there is a little bit more decomposition that has taken place because we're starting to get more of a pale brown color within the reaction vessel. As the reaction continues in our third picture, we now have a very dark brown color, and that tells us that there's a large extent of NO2 found in the bottle. And then finally, you can see the colors look the same within the bottles, and so now we can tell, because there is no longer a change in the concentrations, that we have established equilibrium. At equilibrium, we know that the rate of the forward reaction is equal to the rate of the reverse reaction. If we were to write each individual reaction out, we would say that the forward direction would be N2O4 yields 2 NO2, and the reverse reaction would be 2 NO2 forming N2O4. If we were to use our kinetics information and write out our reactions, we would say that the rate of the reaction is equal to K times the N2O4 raised to the first power, and we could say that the rate for the reverse reaction will be equal to the K for the reverse times the NO2 concentration squared. We could then rearrange our equation, knowing that the two different rates are equal to each other. We could then set both of our rate expressions equal to each other. I could then take this rate expression, divide by K for the reverse on both sides, and then also divide by the N2O4, and that comes up with a new expression. When we look at this, and I apologize again because we have another constant K, but please notice with this K, it is a capital K instead of a lowercase k. This K is what is known as the equilibrium constant for a reaction. This constant will tell us how far in the forward direction the reaction will persist before it achieves equilibrium. When we look at the generalized reaction, AA plus BB forms DD plus EE, the equilibrium expression for this is going to be written out as the concentration of your products raised to the power of their coefficients divided by the concentration of the reactants raised to the power of their coefficients. The first thing I want to mention before we start getting into anything specific with the equilibrium constant is please do not get confused when you see the little subscript below the K. This is going to be representing specific types of scenarios where we're going to be looking at a very specialized reaction. So when we look at it for the KC, that one is talking about the equilibrium constant in terms of concentrations. If we have a total gaseous system, we can look at the partial pressures of the gases because that is proportional to the concentration. We can use the partial pressures of the gases raised to the power of their coefficients, and we would list that as a Kp instead. By the time we're all done, we have a generalized KEQ, or just a K without a subscript. You're going to see KSPs, KAs, KBs, KWs, KFs. They all are representing the same concept. It's just that they're talking about a specialized reaction. But in all those cases, we're still talking about the product concentrations divided by the reactants concentrations raised to the power of their coefficients. So this again is just a generalized reaction that we would have. The last thing I want to mention, when it is a concentration, remember that the brackets that we write represent a molarity. So to show a difference when we have a concentration being given versus a partial pressure, you'll notice here we have the brackets for partial pressures. As you see down in the bottom, we use parentheses. So that will tell us when we're using the pressure. So just remember, parentheses start with a P, as does pressure, so those two things go together. So let's now take a look at some examples of how we write out the equilibrium expression. It's very simple. Again, we take our products and put them in the numerator, raise them to the power of their coefficients. So in this case, if I'm doing this in terms of a Kc, I would take the concentration of the NH3 and I would square it because its coefficient is A2, and then I would divide it by the concentration of N2 and the concentration of H2, and since its coefficient is A3, we would cube it. If we are doing this in terms of partial pressure, since it is a completely gaseous system, I could take the same thing, just put Kp down, and I would put NH3 squared, and I do partial pressure, and then I would do the partial pressure of N2 times the partial pressure of H2 concentration cubed. These values are not going to be the same when we talk about it in terms of KPs and KCs. Later on in college or in AP Chemistry, you will find a correlation between these two and an equation that we can use to convert between them, but it's not something you will need to do. As we look at our second system, notice that all of these are aqueous. So as a result of that, I cannot do the Kp because they will not have any partial pressures. So all I can do for this one is a Kc, and my two products, I would have H plus and I would have Cn minus, and then I would have the HCN in the denominator. All of our coefficients are 1s, so they're not raised to any other power other than 1. We are now going to focus on writing equilibrium expressions for heterogeneous equilibria. Instead of having the same state of matter for all of our reactants or products, we are now going to look at reactions that involve more than one phase. Only aqueous and gaseous substances will be included in our equilibrium expression. For solids and liquids, their concentration is essentially their density, and at the same temperature, densities are constant for the solids and liquids. So if we were to write out this expression just in general, we would begin by saying the concentration of the KCl squared times the concentration of the O2 cubed divided by the concentration of the KClO3 concentration squared as well. However, when we put in that Kc value, we're basically going to take that and have that multiplied by the KClO3 concentration squared. Oops, sorry, that should just be K there. The concentration squared divided by the concentration of the KCl squared, and that's going to become our value for the Kc. So the densities of those substances will already be incorporated into the value for the Kc. So the actual equilibrium expression I would have would just be Kc will be equal to the concentration of the O2 raised to the third power. As we look at our bottom example where we have the electrolysis of water taking place, we're breaking down liquid water, forming hydrogen and oxygen gas. So for this one, we would just simply write Kc is equal to the concentration of the H2. Again, it has a coefficient of 2 squared times the concentration of O2 to the first power. So that would be my final answer and my final answer. Okay, so now let's have you guys try a few. So take a moment and pause the video and see if you can write out correctly the equilibrium expressions for these particular reactions. Okay, so hopefully you've taken a moment to try to write these down. We're going to do these equilibrium expressions in terms of the Kc. So for this first one, you'll notice we have a homogeneous system. I have gas, gas, and gas for my three reactants and products. We need to balance our equation for this. So in this case, when we do this, we would have a 2 in front for the N2O5. I would place a 4 for the NO2, and then I would have an O2 to finish with. You'll notice here I have 4 N's, 4 N's, I have 2 times 5, 10 oxygens, 4 times 2 plus 2, 10 oxygens on each side. So my Kc for this particular reaction, I would have the concentration of the NO2 raised to the 4th power times the concentration of O2, and then I would divide that by the concentration of N2O5 raised to the 2nd power. For our second example, we need to balance our equation, so I'd have 2 for the sodiums, I would have 2 for the waters, and 2 for the sodium hydroxides, and then 1 for the hydrogen gas. We now have a heterogeneous equilibria, so notice I have a solid and a liquid, so both of those would be canceled out from our expression. So I'd have Kc is equal to the concentration of the NaOH squared times the concentration of H2. And then finally, for our last reaction, we have another homogeneous system. I have the combustion of propane. So with this one, to balance the equation, I would have a 3, a 4, and a 5 for my coefficients. So for this last one, we would say the Kc would be equal to the concentration of carbon dioxide raised to the 3rd power times the concentration of water raised to the 4th power divided by the concentration of the propane gas and the concentration of oxygen gas raised to the 5th power. So let's look at one more example problem here, or two more example problems. For this first problem, we have the reaction 2SO2 plus O2 forms 2SO3. Which of the following is the correct equilibrium constant expression? So for this, remember, we have products over reactants. So I need to have SO3 in the numerator, and I need to have SO2 and O2 in the denominator. Both of them, or all three of them, are gases, so all of them will be included in the expression. So anything with SO3 in the denominator, we can cancel off as an answer choice. So I can get rid of A, and I can get rid of B. So now I have to decide between C and D. So both the coefficient for the SO2 and the SO3 are 2, but remember, we're raising those to the powers of those coefficients, not multiplying them by those coefficients, so we can eliminate D as a answer choice as well, and that leaves us with C. As we go on to the second problem, writing out a couple more equilibrium expressions. So for our first one, for A, we would have the Kc for the reaction being the equivalent of the Hi raised to the 2nd power times the concentration of H2 and the concentration of I2. And for B, we would have the Kc for the reaction. This is now a complex ion. That's something that we haven't talked about yet in chemistry class. But we'd have CdBr4 2 minus divided by the concentration of Cd2 plus and Br minus to the 4th power. Okay, so now we're going to discuss the equilibrium constant. The value for K will always be the same at a given temperature, regardless of these amounts of reactants and products that are initially present. The reaction will always shift in a certain direction so that whatever changes we make, it will always come up to give you the same ratio of reactant to product concentrations. So you'll always have one value for the equilibrium constant at a particular temperature, but you can always have an infinite number of reactant and product concentrations. We're now going to discuss the magnitude of K, what it means when we see the K value. So if we have a reaction where the K value is much greater than 1, that means that in that system we're going to find mostly products. And so we would say that the reaction favors the products, or the equilibrium lies to the right. If your K value is much smaller than 1, that means that the reaction is reactant favored, which means that inside of that reaction vessel at equilibrium, we would find mostly reactants inside. If your K value is equal to 1, then that means that you have relatively equal concentrations of both reactants and products. So we can talk about this as far as how far along the reaction will progress once equilibrium gets established. So if I have that K value being greater than 1, then that means that we're going to go almost to completion by the time the reaction hits equilibrium. If the K value is less than 1, then that means that the equilibrium will be established very shortly within that reaction process. Not talking about a kinetics time frame, but just simply as far as a conversion of reactants to products. So the rate of the reactions forward and reverse will become equal when very little of the reactants have been converted into products. So we're going to look at a reaction here in terms of the production of ammonia. So we take nitrogen gas and hydrogen gas and form ammonia gas as a result. Now, as we're looking at this, we can infer some information from the graph. So we have our equilibrium concentrations for each of our different substances involved in our chemical reaction. I'm going to set up our Kc reaction. So once more, we did this one as an example problem. I'd have NH3 concentration squared divided by the N2 concentration and the H2 concentration cubed. As we look at the graph here, we don't have exact numbers for our concentrations, but we can infer some information about what generally we would expect from a K value. So for this particular reaction, you'll notice that I have the N2 being my lowest concentration, and again having the most gentle slope out of the three because its coefficient is only a 1. The hydrogen had the steepest slope because its coefficient was 3, so it was being consumed 3 times faster than the nitrogen was. And you have the NH3 in the red that is forming as the reaction proceeds. At equilibrium, I still have the highest concentration of the H2, the lowest concentration of N2, and a concentration in the middle that is the NH3. Now, from our expression, knowing that the NH3 is in the numerator and its concentration is squared, we can then look at that and divide it by the concentration of the N2 and the H2 cubed. Since H2 is my largest concentration at equilibrium and its coefficient is a 3, so I would be cubing that value, we could make the inference that the Kc for this reaction would be less than 1. So that means that in the reaction vessel, we're going to have a larger concentration of the reactants compared to the product. I do realize that the N2 is a smaller concentration, but we're talking about the combination of both the H2 and the N2, not each one individually. So the product of the two reactant concentrations is going to be a greater amount than the product concentration in the numerator. Okay, so we're now going to use this example to determine the actual value for the equilibrium constant when you have pressures or concentrations that are known. So you'll notice again it's giving you a specific temperature. That is irrelevant. That is just telling us that, again, the K will only change with a change in temperature. So now it tells you I have a partial pressure of hydrogen gas, a partial pressure of nitrogen gas, and a partial pressure of ammonia from this reaction. So when I set up my expression in terms of Kp, remember for partial pressures we put the brackets. I have the partial pressure of the NH3 squared. I then have the partial pressure of N2 and the partial pressure of H2 cubed. So I can now plug in my values, and I would just simply say for the Kp, I would take the 0.166 squared, and I would divide that by the 2.46 and by 7.38 concentration cubed. And when we plug those in, we get a value that is equal to 2.79 times 10 to the minus 5th power. So you can kind of see here by the values for each of the partial pressures that we have a majority of the reactants in equilibrium within that vessel. So again, the K being less than 1, 10 to the negative 5th being a much smaller value than 1, we know that this is a reactant favored reaction. Okay, so I just want to illustrate that no matter what the concentrations are for a particular reaction, if it's being done at the same temperature, you're going to end up with the same value for K. So as I look at this reaction, I have a homogeneous system, all aqueous reactants and products. So if I were to set up my equilibrium expression, Kc, I would have the concentration of the FeSCN2+ divided by the Fe3+ times the SCN- concentrations. So if I were now going to take these concentrations and plug them into the expression, the first one that I would have, Kc, would be equal to 9 divided by 1 and 5. 9 divided by 5 is equal to 1.8. As I look at the second trial, my Kc would now be equal to 10.80 divided by 3 and divided by 2. So 10.8 divided by 6 also equals 1.8. And for my third trial, we have 6 in the numerator, dividing that by 0.37 and by 9.00, and when we do that, we end up with 1.8 as well. So again, at the same temperature, your K value, and it is an experimentally found value, so even though it will be the same, it might be 1.78 for one just because of the rounding of the concentrations. So you should always get somewhere very close in the ballpark to the same K value for the different reactions. So Kc, in this case, 1.8 for each one. Okay, so let's look at one more example. We're going to calculate Kc for this particular reaction. So the first thing you always need to do is set up your equilibrium expression from your balanced equation. So I would have the Hi concentration raised to the second power divided by the H2 concentration and the I2 concentration for this particular reaction. So now it's asking us here to determine the Kc for this reaction. It tells us that the value for the Hi is 1.87 times 10 to the minus third. So I would take that concentration and square it. And then I would take the concentration of the H2, which is 1.000 times 10 to the minus third, and I would multiply that times the concentration of the I2, which is 2 times 10 to the negative third, and I would solve. So when I take this and multiply 1.87 times 10 to the minus third squared and divide it by that, we end up with 1.75 for our K value. Noticing here that our concentrations are relatively equal between the three substances, that plays out where you notice that I have my value equaling 1.75. So I have roughly equal components of the reactant and product concentrations. Just realize, again, I only have one product, but since it is squared because of the 2, that makes up for the difference with our different exponents because I have 2 10 to the minus thirds for my reactants. So we are now going to shift our focus to the factors that affect the equilibrium of the system. So we're going to deal with something that is called LeChatlier's principle. And LeChatlier's principle says that if a change is imposed on the system, when we talk about that change, you'll see that also termed as a stress. So when you have a stress on the system at equilibrium, the system is going to shift in a direction that will reduce that stress or that change that has been applied. So everything here, we're changing the components of the system, so they want to change back so that they will once again have the same ratio. So we have three factors that are going to affect the changes on the system. The first one is a change in concentration, and with the concentration, you'll have the system always shifting away from where you have added a component. If a component is removed, the reaction will shift towards the side that it was removed from. The second one is a change in temperature. This is the only one that will actually change the value for K. K will change when the temperature changes. If it's endothermic, energy is going to be a reactant. If it is exothermic, energy will be listed as a product. In terms of thinking about the shifts, you can treat temperature just like it is a concentration. Okay, so I wanted to give you an example here for a change in concentration or partial pressures within a system. You'll notice here again we have our reaction, N2 plus 3H2 forming 2NH3. So you'll notice here on the far left side of the graph, I have straight lines representing constant partial pressures for the N2, the H2, and the NH3. And then you'll notice in this first dotted line, I have disrupted my system or disturbed my system. I've added a stress by putting in additional hydrogen gas. So you'll notice the partial pressure initially spikes for the hydrogen gas, which then causes the N2 to drop. And I hope that makes sense, because in order to use up that additional H2 that we have added, I had to combine that with some of the N2. So you'll notice from that initial spike in the partial pressure, the concentration of the H2 drops, but so does the N2. And then finally, the NH3, because it's being produced, its partial pressure increases until once again equilibrium is established. Now, when that happens, the ratio of my reactants and products will still come out to be the same value of K as we had at this initial equilibrium position. So again, the only thing that changes the value for K is temperature. Now, you will see, depending on the source or the site that you look at, a lot of people always try to explain LeChatlier's principle thinking about like a seesaw or a balance, shifting around weights to make one side become equal and reestablishing the balance. I'm not going to do that. You can use it in terms of the reaction. I'm going to write it over here again on the side just so you can kind of see. As we were talking about on that previous slide, by adding the extra H2 gas on the reactant side, I have now created the stress that's affecting the reactants, and so in order to get rid of the stress, I have to get rid of some of that extra H2, so I'm going to have my reaction shift further to the right, which will cause more of the NH3 to be produced, lowering the N2 and the H2 as a result, and it will reestablish the value for K. So you can just simply say, okay, I'm adding it on the reactant side, so it's going to shift away towards the products. If I were to remove, say, N2 from the reaction, now it's going to break down more of the NH3 and have the reaction shift to the left to have it make up for that loss of the N2 gas. I much rather prefer looking at changes in concentration from a mathematical standpoint. Since I know the K is equal to my products raised to the power of their coefficients divided by the reactants raised to the power of their coefficients, we can look at something which we call a reaction quotient. That reaction quotient is the exact same thing that we have for the equilibrium expression, except we're using Q instead of K. This would be for non-equilibrium conditions. So I would still have the same thing. Q would be equal to the products raised to the power of their coefficients divided by the reactants raised to the power of their coefficients. It's just for whatever the initial concentrations are, and it allows us to determine the direction that the reaction will shift. So if I have a scenario where my Q is greater than my K, that would mean that I would have too much product that would be present, and so as a result, the reaction will shift to the left. That way it will lower the amount of product, making my number in the numerator smaller, and would make my number in the denominator larger. So the ratio would become smaller until my Q is once again equal to K. When the Q equals K, that means that the reaction has reestablished equilibrium. If my Q value is less than K, now I have too much reactant that's present, and so as a result, my denominator is larger than my numerator, so I'm going to shift the reaction to the right, which will increase the value in the numerator and decrease the value in the denominator. And so as a result, it would once again reestablish the equilibrium. So if you want to think about it just in generic terms of the addition of H2, that would increase the amount of my reactant concentration, which means once again that my Q would be less than K, so I would have to shift it to the right in order to reestablish equilibrium. So as we look at the effects of a change in concentration, we have a second example here where we take phosphorus trichloride, PCl3, react it with chlorine gas, and it will form PCl5 as a result. Any of these possible changes would cause a shift in the reaction to the right. So I could increase the concentration of the PCl3 or the Cl2, because again that would make my denominator larger, so it would cause a shift going to the right, or I could decrease the amount of the PCl5. By decreasing the amount of PCl5, my numerator is smaller, so my ratio again of reactants and products would be smaller than the value for K. So it will shift to the right to reestablish the equilibrium. On the bottom in the red, any of these changes would cause the equilibrium to shift to the left, and so you could have either a decrease in the PCl3 or the Cl2. In either case, my reactant concentrations would drop, meaning that my ratio would become larger, so now my Q would be greater than K. And then same type of thing, I would have my increase in the PCl5. That would also increase the value in the numerator, which would then make Q greater than K, causing the reaction to shift back towards the left. Okay, so we're now going to look at changes in volume. And when we talk about changes in volume, just remember that volume and pressure are inversely proportional to each other from our gas laws unit. So what that means is that when we decrease the volume of a gaseous system, that is going to increase the pressure of the system. And so according to LeChatlier's principle, the system is going to want to shift in the direction that would produce a smaller amount of pressure. You have to remember from our gas law unit that pressure is directly proportional and created by collisions between the particles and the container walls. So when we look at our first reaction, we have our key over here for our substances. We have N2, H2, and NH3 listed over here on the right. And you'll notice in our first compartment chamber, I have 4 H2 molecules. I have 1, 2, 3, 4, 5, 6, 7, it appears. 7 N2 molecules, and I have 1, 2, 3 NH3 molecules. So you'll notice with this piston we are compressing it, so we are dropping the volume, which means that we're increasing the pressure. So we have an increase in the pressure, and so the system is going to want to shift in a direction that will relieve that stress. So again, looking at our chemical reaction that we have, N2 plus 3H2 forming 2NH3. You'll notice for this that I have 4 moles of gaseous reactants. I have only 2 moles of gaseous products. So for this reaction, the system is going to shift when we increase the pressure to the side of the reaction that has the fewest number of gaseous molecules. So you'll notice as we shift that volume, and we now go to the container C when the equilibrium has been reestablished, you'll notice that I now have 1, 2, 3, 4, 5 NH3 molecules. I have 1, 2, 3, 4, 5, 6 N2 molecules, and I have only 1 H2 molecule. So 3 of the H2 molecules and 1 of the N2s were converted into 2 extra NH3s. So if we look at the total numbers in the container, I started with 14 total particles in this first chamber, and I now have only 12 particles in this second chamber. And so as a result of that, I have reduced the total number of particles, so my number of collisions would be decreasing, which would drop the overall pressure and reestablish equilibrium. Okay, so we're just going to finish up the effects of changes in pressure on the system. Now, when we look at the system, same type of thing as concentrations. If we add a gaseous component, the reaction is going to shift away from where that reactant or product was added. If a component is removed, then the reaction is going to shift towards the side of the removed substance. A couple of other little things here. If we add a inert gas, and inert means again non-reactive, so something that is not taking part in the reaction itself, then there will be no effect on the equilibrium position. Because the equilibrium position is based off of the partial pressures, even though the total pressure would change, the partial pressure of each of the individual gases within the system stays the same. And so as a result, there would be no effect on the equilibrium position. And then finally, decreasing the volume, which would be again increasing the pressure, that is going to shift the equilibrium to the side that contains the fewest moles of gaseous particles. The last thing is if we have that heterogeneous system, if we would add more of a solid or a liquid that is a part of that equilibrium system, it would also have no effect. So I'm going to add one more. So adding an additional solid or liquid to an equilibrium system will have no effect. Okay, so the last effect is on the change in temperature. So once more, the value of K does change with temperature. So for LeChatlier's principle, we have to look at how the reaction is going to shift when the temperature changes. So for an exothermic reaction, we can treat heat as if it is a product. So if we increase the temperature, the equilibrium is going to shift towards the left. So as a general rule of thumb, increase in temp always shifts in the endothermic direction. So if I have an endothermic reaction, energy is being absorbed or consumed, so heat is a reactant. So adding the temperature to the system, adding the energy to the system will cause the system to shift to the right, away from where the heat is located in the reaction. Same thing if we remove it, if we put it into an ice bath instead of putting it into a hot water bath, now the reaction would always shift towards the exothermic because we want to replace the heat that's lost, and producing the extra heat will be the reason why it will do that. Now, I want to just show you a generic example of a reaction here so that you guys can kind of get a sense of what we're talking about. So I'm just going to put a AB forming C plus heat reaction. Now, in the forward direction, you can see I would have just the same as written. A plus B forms C plus heat. If I were to look at that in terms of the reverse reaction, however, I would now have C plus heat forms A plus B. So you can see from any particular reaction, there's always going to be an exothermic reaction and an endothermic reaction for each individual reaction. So we can have a shift in either direction depending on whether heat is being released or absorbed from the system. So in this case, because heat is found in the forward direction as a product, again, it would be an exothermic reaction. So it always wants to move. If we increase the temperature, it always wants to move in the direction that will consume the extra heat, which is the endothermic direction. So you can see here the endothermic direction is taking the C plus heat and forming more of the A plus B. So for this overall reaction on the top, increasing the temperature would cause the reaction to shift back towards the left. If I were to decrease the temperature, now we want to replace the heat that was lost, so we're going to try to produce more of the heat. The production of heat comes in the forward direction for the reaction, since heat is a product, and so decreasing the temperature will now cause the reaction to shift to the right. So if we had an endothermic reaction overall instead of an exothermic reaction, then the two things would be just kind of flipped for what the overall direction would be for the reactions, but it would still follow the same process as in the endothermic direction being favored when we are adding heat to the system, exothermic reaction being favored when we release heat from the system or take away heat from the system. Okay, so we're going to do a quick practice problem for LeChatlier's principle. This question says, one method for the production of hydrogen gas can be described by the following endothermic reaction. So we can place heat on the reactant side. So I'd have CH4 gas plus H2O gas forms CO gas and 3H2 gas. How many of the following changes would decrease the amount of hydrogen gas that's being produced? So for our first example, we would be adding extra H2O gas. You'll notice H2O is a reactant. So again, for my Q concept, products over reactants, I'm increasing the amount of the reactant, which would make my reactants larger. So my denominator would be larger, which means that Q would now be less than K. So I need to increase the amount of the products in order to reestablish the equilibrium. So as a result, by adding the extra H2O, it would shift the reaction to the right, which means that we would now be increasing the amount of H2 gas that would form. So choice 1 is not a valid example. For the second choice, the volume of the container is doubled. So that would mean that we would have a decrease in pressure. So remember, for pressure, we're going to have the reaction shift in a decrease of pressure to the side that contains the most moles of gaseous reactants or products. You'll notice I have 2 moles of gaseous reactants. I have 4 moles of gaseous products. So that would cause the reaction to shift to the right once again, and that would increase the amount of H2. So therefore, choice number 2 is also not valid. And then our last one, we have the change of the methane gas, CH4, being removed from the reaction vessel. So in this case, by removing the CH4, we are now going to have a smaller value for the denominator for Q. So therefore, I would have too much product compared to reactants. So to reestablish the value for K, by subtracting the CH4, the reaction is going to shift to the left to replace it. So that would mean by shifting to the left that I would be reducing the amount of H2. So that would be a correct choice. So our final answer would be A. So the last concept that we are going to cover is what we call our solubility equilibria. So when we look at this, again, the solubility equilibria is dealing specifically with insoluble salts, meaning again that they cannot dissolve to any great extent in solution. Now, these will quickly form a saturated solution. We talked about this before. When we look at this, the saturated solution again tells us the max amount of solute that will dissolve in a solvent at a given temperature. So when we look at this value for KSP, that is going to be the product of the two dissolved ions multiplied together. This one's going to be a little bit different than our normal type of reaction that we've talked about so far. When we deal with the KSP, we are looking at some type of salt, in this case the solid. So notice I have a heterogeneous system because that solid is going to break down to just a very small extent when dissolved in water into some M+ aqueous and X- aqueous ions. So my KSP expression, remember when we have solids or liquids, we disregard them. So I'd have the concentration of the M+ times the concentration of the X- being my value for the KSP. Now, for a different insoluble salt, say I gave you something like, let's do silver sulfate. So if I were to place silver sulfate into water, I would get a very small amount that would produce silver ions and sulfate ions. So I would have, for the balance equation, since I have 2 atoms of silver for every 1 sulfate based on their charges, now when I set up my expression, I would have the concentration of Ag+ squared times the SO4 2-. For these problems, you'll never have anything in the denominator because it's always going to be a solid. But the one thing that does change, because the concentration of our products is directly related to the formula for the initial salt, we have to take into account the differences in the molarities based off of our coefficients. So for example, if I started this as a 0.002 molar solution of the silver sulfate, because I have a coefficient of 2, my concentration of the silver would be 2 times the 0.002 or 0.004, and the concentration of the sulfate would be 0.002. So let's take a look at a second problem that we have. So when we look at this equilibrium constant, again, it's going to have only one value for a given solid at a given temperature. So my KSP for this particular reaction for the bismuth sulfide, notice I have Bi2S3. So this is going to break down into 2 Bi3 pluses and 3 S2 minuses. So I would take the concentration of the Bi3 plus. You need to put the ion's charge in with the substance, and I would square that. And then I have the sulfide ion S2 minus raised to the 3rd power. You have one of two ways that you can have these types of problems given to you. They can either give you the value for the KSP and ask you to solve for the molar concentration, or they could give you the concentration of the reactants and ask you to solve for the KSP value. So again, if you're given KSP and you're trying to solve for the concentration, now it's going to change just a little bit because, again, knowing my coefficients, This coefficient for the solid is always a 1, so I could label this as being a 2x for the concentration and a 3x for the S2 minus concentration. So when I would set this problem up, I would have it equal to 2x concentration squared times 3x concentration cubed. So that would give me 4x squared times 27x cubed. So again, 3 times 3 times 3, 27x. So that would tell me total that it would be equal to 108 times x to the 5th power, equaling the KSP. So then to solve for that value, whatever the KSP is, you would divide it by 108, and then you would take the 5th root of that value. So we're now going to look at one more application of LeChatlier's principle that's involving something that we call the common ion effect for these insoluble salts. So if I have one of these insoluble salts that's already present in solution, and then I add a soluble compound that contains that same ion, it's going to cause an increase in the concentration of one of the ions and will cause the reaction to shift towards the side of the solid. Now, for this particular graph over here on the side, you can see that I have a molar solubility of calcium fluoride being an insoluble salt. So I'd have CaF2 as a solid. That would break down into Ca2 plus and 2F minus ions. Now, you can see on the bottom, I have increased the concentration of the sodium fluoride. So when sodium fluoride would dissociate, I'm going to write that down on the bottom. So when I have sodium fluoride dissociating in water, it is completely soluble. So I'd have Na plus, and then I'd have F minus ions that would be produced as well. Since the F minus ion is completely soluble from the sodium fluoride, it will increase the concentration of the F minus ions that are present in the solution. Since these would be in the same container, this F minus would be the example of adding the additional concentration of the F minus in our initial equilibrium system with the calcium fluoride. Because I've added extra F minus ions, that would cause the reaction again to shift away from that additional F minus ion and would produce more of the solid CaF2. So it would reduce the solubility of the calcium fluoride. Okay, so we're now going to actually look at how to calculate the KSP value from the concentrations that are given. So the first thing that I want you to always do, once again, is to set up your balanced equation. So for this, we would have PbCl2 as a solid going into water, and it would form Pb2 plus and 2 Cl minus ions. So my KSP expression would therefore be Pb2 plus times the Cl minus concentration squared. Now, in this particular example, they tell us what the concentration is for the Pb2 plus ion. So you can see it says that the Pb2 plus is 1.6 times 10 to the minus 2 molar. And so we can infer, based on my molar ratio, 1 to 2, that the concentration of the Cl minus would be 2 times the 1.6 times 10 to the minus 2, which would be 3.2 times 10 to the minus 2. So now I have concentrations given for each of my two products, so I can simply plug those values in. So I'd have the 1.6 times 10 to the minus 2 times now the 3.2 times 10 to the minus 2, but that would be a concentration squared. So now when I plug my values in to the calculator, we end up getting 1.64 times 10 to the minus 5th power. So our correct answer would be D. Now, I'm going to use this problem really quickly just to illustrate that concept that we're talking about with the common ion effect. So if I had this same solution here, but I added an additional 0.10 molar NaCl to the solution. Now, I know that the NaCl would have a concentration that would be the same for both the Na plus and the Cl minus because I have a 1-to-1 ratio. So if I had 0.10 molar NaCl, that would give me 0.1 molar Na plus and 0.10 molar Cl minus. So now I could take this new concentration, because that is going to be completely soluble, and I could plug that back into my expression. So knowing that the KSP value would stay the same, 1.64 times 10 to the minus fifth, I could now have that equal to the new Pb2 plus concentration, because that additional Cl minus would cause the reaction to shift to the left, decreasing the amount of the Pb2 plus, and then I could have the 0.10 molar concentration squared. I don't need to multiply this times 2 because my source of the Cl minus has a coefficient of 1 from the sodium chloride, so it's going to have a total concentration of 0.1 molar. So if I were to set this up and now divide by 0.10 concentration squared, I would have my new Pb2 plus concentration equal to 1.64 times 10 to the negative third power, if you type that into your calculator. So you can see my Pb2 plus initially was 1.6 times 10 to the minus 2. Now it's gone down to 1.6 times 10 to the minus 3 as a result of the additional Cl minus. So again, this is not something that I would ask you to do. This is a little bit more advanced, but I just wanted you to see, mathematically speaking, how that common ion effect can change the concentration of one of your product concentrations. So now let's look at the other type of problem, where you are just given the KSP and you're asked to calculate the solubility. When you solve for X, that always equals the molar solubility for the compound, because its coefficient would always be a 1. If we have one of our ions having a coefficient, then its solubility would have to be multiplied by whatever that value is for X to equal its concentration. So in this case, we have AgCl for silver chloride, so that would break down, with that being a solid, into Ag plus and Cl minus for the ions. So you notice I have a 1-to-1 ratio. So my KSP in this case would be equal to the concentration of Ag plus and Cl minus. Because each one has a coefficient of 1, I can just set their values equal to X. So I'd have X and X. So I would have 1.6 times 10 to the minus 10th equaling X squared. So to solve for the molar solubility, I would just take and take the square root of the KSP value, and 1.6 times 10 to the minus 10th square rooted would be 1.3 times 10 to the minus 5th. So our answer would be A. Okay, so let's look at one last example problem just to illustrate the concept that I was talking about on the previous slide. For this one, we're going to calculate the solubility of the magnesium hydroxide in water, but we're also going to determine the concentration of the Mg2 plus and the OH minus ions in solution. So for this problem, setting up our KSP expression, notice I have a 2 for the coefficient for the hydroxide, a 1 for the magnesium. So I'd have the concentration of magnesium times the concentration of the OH minus squared. So again, because I have twice as much hydroxide produced as I have magnesium, I'm going to set magnesium equal to X. I'm going to have hydroxide set equal to 2X. So I can now take this, 5.6 times 10 to the minus 12th equals, I would have X times 2X quantity squared, which is 4X cubed. So the first thing I'm going to do is divide both sides by 4. So that would give me 1.4 times 10 to the minus 12th power equals x cubed. So now I'm going to take the cubed root of everything, and I find that my x is equal to 1.13 times 10 to the negative 4th molar. So that x there, that would define my concentration of the Mg2 plus, and also for the MgOH parentheses 2. Now, to solve for the OH minus, I know that the OH minus is equal to 2 times x. So I take 2 times the 1.13 times 10 to the minus 4th, which would equal 2.26 times 10 to the minus 4th for its molarity. Okay, so that ends everything with our equilibrium unit. There is a online learning assignment that you will need to complete for this week. Good luck. I will see you on Thursday to answer questions.